sum of all the stars. This is certainly true. We will see it is not a trivial sum, but I can certainly imagine the global light that I get for this big object will have to do with how well I can trace the individuals. This is an historical spectrum that probably was taken at the Lick observatories, where there was a key player in this business, Professor Sandy Faber. And you see that when you take actually a real observation, there is a huge complexity coming up, okay? And what you see is the results of the addition of all your microstars that you have got in this galaxy. Now, in this case, it is still true that this spectrum is originated by some combination of all the stars in it. This galaxy in particular have basically no flux in the ultraviolet. Then you start to rise up a spectrum, which is featured by a lot of lines which traces elements or blend of them, and this is maybe part of the complication, which in principle we see in the globular cluster of the Milky Way. And in principle we know what they trace. So the art was to think, can we model this complexity? The story started in the 70s. This is Sandy Faber, who in one of her first work, she wanted indeed to use galaxies to measure potentials. And so she needed to determine very well the strengths of selective absorption lines, not even yet to make a conclusion on galaxy evolution, but to measure the stellar potential where the galaxy was embedded. And she put out this idea of observe the stars, and put the coefficient in front of it, arbitrary completely at that stage, and then mix it up and minimize the reduced chi-square or some statistics, such that at the end you get a match to your observed spectrum. This became known as optimized population synthesis. Other key player in the game, but one is Brazilian, you know him, Eduardo Bica. And the other is Bob O'Connell in Virginia, wanted to synthesize especially the UV, and he thought, okay, I just focus on this side, I get a bunch of observed stars. As we know from statistics is probably the most degenerate science, you can certainly get a nice fit. Whether it tells you the physics of galaxies is another business. The way Sandy put it forward was to measure velocity, determine velocity dispersion. People are still using this, so I don't want to appear too disruptive to this method. However, the real problem is you get a fit that doesn't reflect a galaxy with real physics. You can't extrapolate it back in time because you don't have a handle of the age, and you don't know how it evolved forward. So it is a fit that solves a few problems, but not all of them. The actual push to cosmology came with stemming what is called evolutionary population synthesis. And I put here the major player, no modesty, sorry for that. But I can explain why. But actually, we owe most of the work to Beatrice Tinsley, who passed away in 1981 due to cancer. And I know the story because my supervisor, Alvio Renzini, was working with her, writing down the fuel consumption theorem that I'm going to tell you. And he told me after she died, she was the brightest scientist he has ever met. And Alvio is quite arrogant. So to say this, that was really meaningful. In fact, she wrote a series of papers in 1972, 10, 15, I mean, I recommend you to read. She put down all the things on how to actually trace even the Hubble diagram with galaxies. So all these things were there. And what she said at the time was, instead of putting arbitrary weight, let's trust the stellar evolution, which is a robust theory. It is going to improve with the year, but if the Regent branch tip lasts 10 to the 3, I use 10 to the 3. I don't use 1 billion year and make a fake spectrum. That was the idea, essentially. Alvio came out trying to reorganize most of their common work in one consistent paper, which I'll comment about later. In the meantime, a young Gustavo Brusual, in 1983, published a thesis in which he also followed Beatrice and took a bunch of the newly calculated isochron, also from the Padua group, and put forward what is called the isochrone synthesis technique, which I will explain. And instead, I also, because I was a student of Alvio, followed the part on the fuel consumption. So it is important. You will see in the literature there are very often comparisons between our two models, because as of now, they are the most different. So it makes sense to explore them. There are other models, but they are very similar to what Gustavo has published. So what is here the idea behind those contributions that you attach to observed spectra or theoretical spectra are actually weighted by energy and time scales that are proper of stellar evolution. No fuss, no fudge. Okay? If I have a phase that this is what is last, I put this in. If the model doesn't work, then I am stimulated to find an answer. But at least I am anchored to proper physics. The cool stuff is that you get different ages, and you start the fun moving up and down, redshift 36, redshift 4.2. You have a tool that allows you to do cosmology. So now let's see how we calculate these models. What we need to know are this series of input physics. I don't like the word ingredients, which sounds like we are making a cake. I don't like it. It's like diminishing. These are input physics, as in galaxy formation models. They are actually more theoretical, I would say. The first thing you need is how many erg per second your star emit, because that you need to integrate. And that comes from stellar model, the things we discussed yesterday. Then you also need to have a good handle on time scales. If you have a red giant and you overestimate the time scale on that phase, you're too red, okay? Needed to balance the time scale, because there are stars, as we saw yesterday, they are very luminous, but they leave nothing. So that is quite a critical thing. Then, because we don't observe the bolometric, you will have a need to distribute on the spectral energy distribution of those stars. As I will show you, you can do a fully theoretical model where these are theoretical input or semi-empirical. And possibly the virtue is in between. These things maybe are relatively well known. What we don't know is the mass distribution. When you have a when you have a generation of people, actually, you don't know how many children, male, female, okay, there are statistics, but let me extrapolate. How many with dark hair, blonde hair? It's a little bit like that. It's quite of a tricky problem. You have a cloud of gas that fragment into stars, and we lack a theory that tells us exactly, given the initial condition, the mass distribution, which we call initial mass function. And this is a problem that the people have scratched their head since a long time, and what we use are empirical determination based on the Milky Way solar neighborhood. And I will come back on that. It's very legitimate because that must have to do with gravity. So these things is probably similar to what happens when you fragment galaxies, because the distribution power law are quite similar. I'll come back on that. From the model point of view, it's just an input. I can go fancy. And in fact, people go fancy and invent initial mass function at their leisure, more or less. The other thing I want to stress is then how you integrate this information. And as I mentioned, there are two main approaches in the literature, and they give you differences. So this is a slide to summarize what one actually does. This is a theoretical luminosity versus temperature diagram of the stars that you can imagine you have in your synthetic galaxy. So each of these points which I connect are featured by an initial mass, a luminosity, a temperature, and a gravity. This is the main sequence, the turn off, and then you go up in some exotic advanced phases. The evolutionary population synthesis aims at obtaining the integrated properties of this thing, and this can be done in following two approaches. As I mentioned, isochrone synthesis is something that was actually taking mostly due to the work of Gustavo 1983, but I should mention Alessandro Bressan, who also did the isochrone synthesis with his own Padova tracks. All these people have essentially replicated this type of approach. And then the school of full consumption, which mostly was boosted at all ages with my paper, instead make a change of philosophy into this, which I would like to explain you how it works. You need to perform an integration. Here, you need to integrate luminosity, essentially. In the mass sequencer we saw yesterday, you have a linear relation between mass and luminosity. The highest the mass, the highest the luminosity. That's the only place in the HR diagram where you have such a well-behaved relation. And so you integrate your luminosity by mass. That makes a lot of sense. What happens in post-main sequence is instead, luminosity run up, not mass. Effectively, the difference in mass between a turn-off and the tip of the Reggian branch is 2% at every age. So the mass does not run, so the luminosity does not increase because the mass is running up. Plus, the time scale here is negligible. So the theorem suggests a change of integration variable in post-main sequence, which we call the fuel. And the fuel is a product of luminosity and time scales. So the fuel is a new which would like to take into account a few facts that you see here. These stars are the most luminous you can find, but they live very shortly. So the actual contribution must feel 2 variables instead of 1. And they have nothing to do with the mass. You can indeed approximate everything to the turn of mass. And this is what we use. So, let me first, before I give you the open calculation, comment on the stellar mass function. You know this guy? Well, I put the name. Ed Salpeter, a very creative scientist. This is a conference in Florence where he was well above 90. I fear he passed away 1 year ago, something like that. So this man, who was a theoretical physicist, at some point in the 50s decided that the only way to solve this problem was to count the stars in the solar neighborhood. And which makes complete sense, because the problem is you don't only need to count the stars, you need to associate the mass to stars, and that's far more tricky. And in fact, one thing that you would like to know is that the original Salpeter determination that here in this plot is extrapolated to very low masses actually stopped around here. He certainly didn't see with any telescope in 1955 any mass below 1 solar mass. Okay, so this is another thing that people used to extrapolate and say, Salpeter is wrong, but he never measured that. Okay, but he drew a line, and so it was sensible to extrapolate that line. Whatever people have shown when the telescope were giving you access to lower objects like Scala, Krupp, and Chabrier, was that there seems to be a change of slope around the critical mass, which vary a little bit, but not too much, and should be around 0.6 solar masses. And so when I calculate my models, I actually include this double slope power law. Okay? I also include for fun a single slope. I also include things like I want to show that this is a free function. However, it has catastrophic consequences for your, but especially mass to light ratio and the chemical evolution on a cosmic scale. As some of you may know, over the past few years, a new very strong debate came up arguing that actually the most massive galaxies possibly should be even super Salpeter, so made by the smallest star, which causes problem also from a philosophical point of view, but I'll come back on that. So, but from your point of view, you have a function, and you apply this function to your integration, which is a convolution integral over the fluxes of all your masses. So I first show the simplest form, which is the isochron synthesis. So you integrate from your lower mass to your upper mass. What is the lower mass? This relates to the study of Zander. Below this we have planets. Planets don't shine, and so we don't integrate. Okay? This difference in my model, I use strictly 0.1 because I notice that using 0.08 doesn't make any sense exactly. But this is a small dependence on metallicity. The upper mass It depends what you are integrated. A typical value is 100 or 120 solar masses. This is specified in the tables. Of course, if you would like to integrate this population 3 stars, they can have a much higher mass cutoff. So essentially, this is very well known. This a little bit depends, okay? But because these stars die very shortly, your model will fade away with them also in a very short time scale. So at the end of the day, all these differences don't matter. And then you integrate by mass over your isochrone. And so we can immediately comment on the pros and cons of these methods. And as you can imagine, because I use the other method, my list of cons is longer than the pros. But in fairness, it is like that. The method is super straightforward. That's the pros, okay? Well, the fuel consumption require a PhD thesis, a bit of elaboration, also to get into your mind. You get an isochrone and you see what you can do. What are the cons? Some of which actually will exploit the knowledge we put forward yesterday. First of all, you integrate your isochrone until it's calculated. If your isochrone stop at certain phases, there will stop your integration, which causes a bit of problem in the 90s because not all evolutionary phases were inserted in the isochrone. Now, what I showed in my PhD thesis was actually even worse. Because the mass doesn't grow in postmain sequence, when you integrate and the mass is too coarse, the mass being, you get into numerical instabilities. And this numerical instability explains what I discussed with Luigi yesterday at lunch, why models that are based on the same stellar evolution do show fluctuation, and I will have a plot for you later. In my thesis, I noticed that you need to have masses, delta mass as small as 10 to the minus 6 to get stable result and get back onto the fuel consumption thing. The other problem is also, let me comment on that, the region bump is a longer time scale on the RGB, Raphael have shown. The isochrone do not trace that. You need individual stellar tracks because you need the lifetime. The isochrone is a mass beam, so it is shown it dilutes the red. So what happens, for example, is models based on this method are usually redder for all population than others because they give more weight or equal weight to the tip, so to the oldest phase, rather than to the bump that is quite low. So this is the other thing. Most crucially, isochrone traditionally until a few years ago have not included any thermally passing asymptotic germ branch phase. So the last phase was the early asymptotic germ branch. And that's it. And that stopped the isochrone, not to speak about planetary nebulae and other stuff. So you are missing a conspicuous part of the population. And that I will come back to this. And finally, I told you yesterday, and Raphael has shown the same, we have clusters in the Milky Way with nearly identical parameters, vastly different morphologies of the horizontal branch. If you have an isochrone, that morphology is fixed. If you instead use the tracks, you can vary it. And for example, in my model, I play with the mass loss efficiency to create grids that have red, intermediate, or blue horizontal branches. So it is more flexible in a way. And this is where I think it gives you some added values. This essentially summarizes what I said, because mass doesn't trace postmain sequence, is not a good integration variable. So I show you this for the history of it. This is the formulation of the fuel consumption theorem, which tells you that at every age of a population, you can squeeze out as much energy for a certain evolutionary phase is J, according to how much fuel you have in that phase. Expressing the 80s, that wanted to express the conservation of energy, so it's something big, applied to the stellar physics. The reason why Alvio wrote this is because at the time, there were people experimenting with this integration, getting absurd results with model fluctuation that were huge, meaning there was too much energy in certain stars and this would change according to the models. And so he was looking for something objective. And So the thing is, if you have a star of 2.3 solar masses, how much is in the core that the stars can actually burn? That is what you get out in volumetric. So this is very clean. These are normalization constant, and these are other functions that I don't want to comment because it takes too long. So this essentially tell you, put the regulation on your flux. I just wanted to show you what the fuel, how the fuel that seems very mysterious to most people look like. In this plot, the fuel is expressed in solar masses. So this is 0.4, solar mass is 0.3, as a function of the age of the population, of the age of your galaxy. And that is the corresponding turn of mass in which I calculate the fuel. And so I don't have exercises, but I have questions for you now. I will leave you alone and ask someone else. No, don't joke. So you see the trend of the fuel. Let's say a high young population as this, but then the fuel decrease. Remember, the fuel has to do with the energetic in post-main sequence, not main sequence. That is absolutely a linear correlation. It decreases and then jump up again. So at the end, you see that a 8 solar mass and a 3 solar mass dominated population will have roughly the same fuel in post-main sequence. Why? This recaps to what I was saying yesterday. If no one wants to have a go, I can tell you. Here you have a lot of fuel in red supergiant, or supergiant phases, helium burning on massive stars. They are big, so they have fuel because of that. They die out at some point, and there is a sort of transition before the star becomes small and start to develop stable red giants with the degenerate core that I told you. But when they do that, the mass that they burn is always the same, which is cool, right? And effectively, when you integrate with an IMF, you have less of these stars than of those stars. So it's actually, the post-main sequence is boosted in all population. That's the explanation. The other question is possibly is, why after 1 billion years, the fuel consumption doesn't change much? Exactly because what we said yesterday. Because after you can build a degenerate core of that remains. And you see no population, all globular clusters have these red branches, the similar number of stars along it. So the evolution is slowed down. And that's why when we do modeling, you guys, when you apply to your observation, well, we better find something going on here, because then everything is quite stable, especially for old population. So the fuel allow you to understand what some people refer to as box, which I always rebel against. There is nothing black, at least in my box, because I show this plot. But I want you to understand what this is, because it's very instructive. So after you do the calculation, you come up. This plot is usually used in lectures. It became very famous as the energetic of stellar population, which tell you that there are 3 periods in a stellar population. Let's see. Now here the stellar phases are split out so that I can follow there. And this is the bolometric relative contribution. A young population, a young galaxy, what we said yesterday, a redshift 5, or a galaxy, a star-forming galaxy, will have most of its contribution due to main sequence stars, massive main sequence, followed by massive helium, central helium burning, and nothing of the rest. And all the population will be, most of the bolometric is generated by main sequence, so red giant branch. In bolometric, they are basically identical, okay? With a bit of helium burning, and nothing much of the rest. And then there is an intermediate niche around the 1 billion year, in which actually, in my models, but this is not the same in other models, and we'll see, the major player is the asymptotic giant branch. This plot was called the phase transition because you see that you have one phase, second phase, and third phase. And so the idea, well, if you could trace this phase, and I'll show later, then you can age date your galaxies pretty well. This is the analogous calculation published in this paper you will see how noisier this is. Close the live streaming when I say these things. This is noise. No, because I don't want, this causes, actually all this discussion is in this paper of a strong debate among these things. But all this fluctuation shouldn't be there, and they have to do with these numerical instabilities. And there is another thing, because overall, the contributions are similar, but you see, this is DAGB, is never above. So there is a difference, which I noticed, is this one. This goes to 40%, and this remains below the main sequence. This has also to do with the tracks which have overshooting, so they spend more fuel. So there are differences that we need to take into account. You all know these things. The ages is the ages are the model age. So you get your minimum. Yes, they are the same. Here I plot out of this point, and there is a reason for this, because below you don't have any post-main sequence phase. The stars go hydrogen burning and quickly supernova. So doing a plot with a fuel consumption, my model extends down, but there is no fuel. That's meaningless. So that's why I plotted from here. They do isochron synthesis, so they do the same method all over the ages. That's why. So this was the bolometric. When you observe galaxies, you want to know, actually, how certain phases will contribute in different bands. And this was just to give you a chance, the U, B, visual, and then K. Of course, as you can imagine, the bluest band will be at every age dominated by main sequence, which is the solid line, with some help from helium burning at young ages, depending on the temperature. The subgiant branch is very hot because it's close to the turnoff, so it also contributes, but all the cool phases will not matter, and it's still true. Then if you turn it to the K band, you have that at 1 gigayear, you have 80% of your flux coming from AGB stars, at least in my models, and then red giant branch stars. Interesting in the visual, you see that the red giant branch give it 25%, and that's the red giant branch bump, and not the tip that is cold. And this is an important feature that you need to have in your integrated models. Now, the other thing that will come up useful to us in the future, for example, the structure of my code is constructed what we call modular way, a naming that Roy has used for his paper. Fine. Which means the three inputs are kept separately. That's why I can easily change, if I want the energetic from the powder or the Victoria tracks, I change this matrix only, but I distribute keeping the same atmospheric parameter if I don't want to change the mixing length. So it's very flexible to make this type of experiment. And this is just to visualize one model at a specific age, which would give you the theoretical spectral energy distribution in log fluxes here, expected as a function of wavelengths from the UV to the near infrared or further, of a population that in this case is 0.5 billion year solar metallicity. How do you use this thing? People use it for everything. You even derive the dark matter content of galaxies. I say this because it's fun, but it's true. the amount of dark matter devised in galaxy depends on the subtraction of the stellar component, which is the one that you see, and you can model, which in turn depend on the IMF. So this is also an interesting point to remember. So essentially what you do, and what we will, tomorrow we'll go through in how you best do your model. I was enjoying discussing with Natasha at her poster. Do you fit the UV? Do you fit the optical? Do you fit all of them? What do you do? We'll do this tomorrow. But this is essentially the tool that you have. This is just to show what is the main parameter in the model remains, in general, the age. The age is what people want to know because it has the cosmological clock that we were saying. So here I plot the model from 1 million year to 10 billion year, and you see the same thing as before. There is a very fast evolution in the ultraviolet at the young ages, and then there is a settle. The near infrared does not even change much at all because the population is young. You don't have cold stars, but the few you have so much luminosity, this is called overshining effect, that you actually get some quite near infrared, independently of dust. There is no dust in this computation, okay? But then what happens is with aging, your ACD become redder. And so this is how you can use it. There are two basic, one basic unit model that we all calculate, and this is the basic of to see the input physics. And this is called SSPs, or simple stellar population, which is a single generation which have the same metallicity. So your model is function primarily of age, the metallicity you impose, the IMF you impose, and eventually, tomorrow morning, the element abundance ratio. Okay? Now, of course, because the universe is complicated, galaxies are complicated, people recognize very early that it's fun also to make a composite model out of these units. And these are called the CSP, or composite, where you add a new variable, which is the star formation rate, which is a function only of T and not of mass, not of the IMF. You can mix it up, I would not recommend it. Let's see what we mean by this, and we will do explicit galaxy evolution also tomorrow and Thursday. It is known, so we do this model to understand galaxies, but the real problem is the galaxy makes stars at different rates. And some galaxies even change over cosmic time. So in a sense, it's a circular problem that we want to fit the models, but we need to put a prior in our models. I will come back to that. So we know that there are spiral galaxies form a star at a steady pace, actually in a declining mode following the starvation of gas. Ellipticals, certainly from my point of view, stopped forming stars long ago, and I was pleased that Raffaele mentioned the same. They are red, and they possibly form Arashi 5, with very little in between. Then you have this episode of merging, late burst, satellite, I don't know, whatever. They give you another mode of star formation on top of an underlying old population. So what do we do with this? We invent another function, which is called psi of t, which is the star formation rate, which would like to approximate the star formation history, okay? And you integrate between two times. 0 is usually the time at which your star formation starts, your galaxy formation starts, in a sense. And f is actually in the model the time at which you look at a certain model. There is much chaos in the literature on the use of the time, which I will come back tomorrow. The time for the model is very well defined. I impose this integral and make a grid of times. And is the time elapsing from the start. No other average or nothing. And then you can start having fun. And I want to mention a few achievements in the literature that became very popular, and I bet you guys use them. Bruce Wall, Tinsley, and Francesca Matteucci put forward this formulation, which is quite logical, exponentially declining star formation. You start with the galaxy Arashi full of gas, the universe was more in the gas, and you start cooking your gas and making stars. Stars die and give you out mass, but it's much smaller than the initial one, so the content of your gas will decline secularly, okay? I'm neglecting input and inflow from the outside, which can happen. But let's discuss analytically. It's logical to make an exponentially declining thing. You have one additional parameter here, which is tau. That's why there are known tau models. Tau gives you the amplitude of half change of your star formation rate. So if you have a galaxy with a tau of 1 billion years, means that in 0.5 giga-year, your Gaussian is halfway through, okay? So very small tau are actually tell you that the galaxy is forming stars very fast on a short elapse in time. Long tau is like a spiral. Do you know the tau of the Milky Way? Just to keep you awake, but I see you are awake, so that's good. Do you know which tau we think is appropriate for the Milky Way? You see that I like it, the galaxy. Roughly 10 billion years. This if you apply this model, as Francesca Mattiucci did, you recover the element abundances observed in the disk, in the stars of the disk. Only if you allow chemical cooking at this level, in a spiral, okay? So there are numbers that are not just up in the air or good for the fit. So this model became very popular. We all propose a grid of this model at our webpage because you can fit this parameter essentially. And this allowed people like Gustavo to say, well, elliptical, we all agree on that, elliptical are consistent with tau models with a very short tau. If I put a long tau like spirals, you get galaxies that are too blue. Another thing that we put forward more recently that has to do with the exponential but reverse the sign became famous as the inverted tau models. And the reason is that it's an increasing exponential, okay? Why is this important and other people find the same results? At high redshift, it seems plausible to think that galaxies have a star formation rate that is declining. Actually, there is a peak of star formation cosmic is a redshift 2. And before that, there is so much gas that there is actually a lot of inflows, collapse, lumps. So what we say in this paper is that it's better to impose a regime of growth of galaxies. If you use this model, this galaxy will never grow. You have to explain how they get to 10 to the 11.5 and 10 to the 12. And I will show you which difference it makes. This now seems to be appropriate for spheroids or star-forming galaxies, also at high redshift 2 to 3. It has implication in cosmology because you need to ask your cosmological model to provide you gas to sustain high star formation and then to quench it. We'll come back to that. Then you can think that there are galaxies that form stars constantly, but that constant cannot be too long because you run out of gas, or your galaxy becomes 10 to the 14 solar masses. Another thing that our colleague Emanuele Daddi put forward is a sort of truncated. This is different from the exponential. Truncated means that there is an event that quenches star formation instantaneously, so it's a step function. We actually found that this is much better for, again, early type galaxy, because in early type galaxy, if you allow even a small tail of recent star formation, you dilute iron, the alpha element, and you make a blue color that you don't observe. Then the big question is what quenches star formation on basically instantaneous timescale is where people are discussing. There could be AGN feedback. You will hear of it today. It can be other things. But in principle, you want to trace your function, and I want to say this because the story is not all written. So everyone that has a smart idea on changing this is a good place where to invest work. This is a paper from MacArthur that just shows you, just about to put only words, how these curves look like in a star formation rate versus age diagram, so the decay of tau models or the increase. And this is actually taken from a paper from Bolzonello et al. You see how the spectra then look different. This is actually from Bolzonello et al. With BCO3 model, just to show. Elliptical galaxy will have mostly red SED. Spiral will start to have ultraviolet emission. Irregular are similar to spiral, even more luminous, but for a much shorter time. And so on and so forth, and you start to have fun. So, if you have fun doing it. So you have your model, robust stellar evolution, your input physics, then you do the single burst, and then you do the composite. Of course, there needs to be progress. Let me get you out of these busy slides, but there has been indeed major progress in the evolutionary population synthesis model since nearly, 2 decades, but basically 15 years. I will have to discuss one thing that has actually affected all the study of galaxies at high redshift. People is still the most debatable point that occupied the archive, is still very, very used. The inclusion of this red phase. You see how stellar evolution can change your feeling on galaxy, I will tell you that. This turned out to be crucial for determining how accurate your stellar mass is of galaxies. So again, implication on the galaxy mass function, dark matter. The other breakthrough was to recognize galaxies, like the Milky Way, do not only host stars with solar chemical abundance. The sun is solar scaled, good for him, but there are other stars already in the Milky Way. There is a pattern halo bulge. And so what we have done, and I would mention another Brazilian colleague that she has also worked on that, Paula Coelho, was to try to modify, to tweak. Some people tell me, you tweak the model. Yeah, tweak. To make some absorption line a function of the element abundance ratio, which turned out to be a cosmic star formation, galaxy formation tool. The things that then was put forward was the data were getting at higher resolution, and I look and the models were at quite modest resolution, so there was a run to update the model to higher and higher spectral resolution. And we are still doing this, but I would say the model now are at quite a good level with respect to the instrument. And then if I have time, I'll discuss that. Any intermediate question that you want to ask? Fine. So, first things, yep. Oh, sorry, I ask and then I don't look. So bad of me. Please.
Thank you. It was not clear to me. The composite population is made like in population synthesis, adding simple stellar population, or is an evolution or physical evolution of the material of the stellar of. You begin with a population and gas, and you evolve, or just add up different simple stellar populations?
Yes, no, I think what you want to ask is whether when you do a composite population, you also take into account that the metallicity will change in the next generation. Is this what you...
Yes, but I mean, if you, for example, population synthesis codes take different simple stellar populations with different metallicities and ages, and they add them. You are doing that to make the composite, or you have some initial conditions with physics and they evolve?
Oh, okay, no, okay. This is the flux of simple stellar population. So to make composite, you always use your single generation. And essentially, you impose some physics that I translate here in the star formation rate, like you keep forming stars constantly in this interval, or you exponentially decline, and then these ages, the ages of the SSP that you allow to be born, will be different. So any composite model will always start from the SSP, from the single burst. No way that the other way around can happen. Which physics you impose in your composite model depend on your choice. These are things that people have published and are experimented, but there is not the end. You can invent other things, like you can make an exponential declining, and then you impose a merging. So you have new gas coming in, and you make another exponential increasing. This actually has been done. So you have flexibility in your fantasy and the galaxy you are tracing. But your input is always the single burst. It has to be. No. You need, well, okay, so you have single bursts of different ages in a grid. From T equal 1 million year, below is pre-main sequence. So the physics is in the single stellar population first. That's the stellar evolution physics. The other physics you put in top is the star formation history. For example, you could also compose SSPs of different metallicity. The experience tells you that this is noisy, because then you don't know which information you are tracing. So it's better to have a mono, but you can also do that. So there are two levels of physics, the SSP physics and the composite. Yeah, hope is good, but we can discuss also later. So, This was taken from a talk we gave in Oxford a few years ago where all of us were there, so it was quite a lively discussion. And I think what we agreed on was that we all agreed that AGB cannot be fully modeled via first principle. We are all completely shaking hands on that. And the reason is that there is mass loss that pushed the stars away from the phase, which even run on dynamical timescales towards the end, which you cannot model. So we also all agreed that the theoretical energetic must be calibrated with data. And this is what I did back in my PhD thesis, and it was also reprised in other works. So we agreed on this point, but the problem is in the details. What you choose to calibrate makes completely different results on your models. What I used at the time, and Corey and Gang use the same thing, is to take globular clusters. Star clusters should be better said. Why? Because they should be the closest things to a single burst, and I want to calibrate my single units. So here I have two problems. I need to know the edges of the cluster well, because that's my need. And also, the data may be scattered because, unfortunately, the Magellanic Cloud clusters have quite a low mass. Of the masses that Raffaele showed you yesterday, the Magellanic Clouds are between 10 to the 5, if we are lucky. And TAC is 10 to the 6. So this can cause fluctuation. Also, there are not so many. They are good enough, but there are not so many. I still think this is the best approach, but what Marigon Girardi and Brusoil and Charlot in separate paper have done was instead to take a region, a field in the Magellanic Clouds, and to try to model in a composite way the result population. This seems very tricky because you need to know the star formation history of the Magellanic Cloud. I don't know it. Actually, I should give a quote of John Peacock that during our discussion that was quite disarming. He's a cosmologist, said that predicting the star formation history of the Magellanic Clouds is like predicting the weather in Scotland, and he's Scottish. And then, of course, there was a debate because people said, but the weather in Scotland is perfectly predictable. It's always rain. Exactly. It was not a good example. Just to relax the atmosphere, but the situation is pretty serious. There are two problems that I have with this approach. First, that is a multi-parametric approach. You not only have the age in your composite, you have the star formation rate. Who knows what it is? Second, this is a dilution. The field is not emphasizing a single stellar phase because you have stars of many other ages, while the cluster, as dispersed as it is, it's more or less a single generation, okay? And then, unfortunately, the experience has shown that most of the difference between our model, not all, but most, originates from taking two different approaches to calibrate. So that is where, actually, we need to think about what we do. So let me go back to why we want to use star clusters, because even if some of them show extended population, they are still simpler than galaxies. For some of them, the extension in age is pretty small. In the Milky Way is actually more a dispersion in metallicity, as it was said yesterday. But in any case, there is not much you can do. Now, the other thing I should know, and this is for every model, because very often I see papers in the literature, they test my models with M33 globular cluster. How do they know what the age of the M33 globular cluster is? So one thing is you want to test the model with things for which you know the properties in advance. The other thing is to apply the model to extragalactic objects. So we know from the talk of Raffaele, and we will know more, there are a family of star clusters that we can use for different model ranges. The Milky Way halo gives us a lot of old clusters, low metallicity, non-solar element ratio, brilliant things to calculate, to calibrate leaking indices model. The bulge clusters has a reservoir of old, metal-rich, and non-solar abundance ratio. Great stuff for elliptical galaxies. In the disk, we have a few intermediate age. I will show you one of these is M67, turn of age 3 billion year, perfect for elliptical at ratio 0.7, which is the 0.8, which the age is roughly 3 billion year. Magellanic Clouds, in this sense, is beneficial because it has a population of clusters spanning from very young to old. The metallicity is not solar, and this was one main, but it's not also not too subsolar, it's what it is. The element abundance ratio is not well known. So, after you pick which family you use, then you can have actually a quite stringent test to your model. Of course, data are data. I do models. Sometimes I believe models are more robust than data, because I've seen data changes over the year. With bad weather, we would have an error bar like that. It's quite tough to fit a model when there is one model when there is an error bar like this. So let's be critical on that. So what people have done for this globular cluster, as I said yesterday, you get an age. The metallicity is obtained by spectroscopy of red giants. So I put my model with that age and metallicity, and it should recover the integrated properties. As simple as that in principle. Of course, in practice, it's more annoying. So for the PhD, at the time of my PhD thesis, the only usable, still they are, globular cluster were in the Magellanic Clouds. So what I've done is in this plot, and I show you what happened. Here I plot with the fuel consumption. That's the thing. With the fuel consumption, you can calculate these things. With the isochron, which at the time did not have any TPHB, you cannot. You calculate theoretically, with the fuel consumption, how much contribution you have varying the fuel such that you match the data. In this way, you have a direct constraint, because these are data, these are the measurement, you get the fuel. If you get the fuel, you get immediately the mass losses intrinsic, because this is observed. So that was the idea. In fact, people have used the fuel to recalibrate their traxes later. And what did happen, and these were actually realistic error bars, it was immediately clear that in the family of Magellanic Cloud clusters, you have young clusters which have very little AGB at the level of 10% or less, old clusters as well, and then you have a burst in which the intermediate age, 1 billion year, were very abundant in carbon stars that, as you know from yesterday, they only form on the AGB. Why do you bother, you would say? I tell you why. Because as clusters, galaxies are not different. So if these calculations are correct, I should expect that galaxies, big galaxies that are roughly 1 billion year in age, like elliptical primordial redshift 3, should actually be filled with these stars. And if I don't put the stars in the SED, I should have problem with it. This was one of the main reasons for including it. Now, the other thing, this is all fine, is energetic. Then you need the spectra. Have you ever seen something more disturbing? These are observed spectra, not my work, but Lanson and Wood, of actual AGB stars. Carbon rich. The two colors point to different temperature, as good as you can determine the temperature of this. This is warmer, this is colder, and oxygen-rich M-type stars. You see immediately from this, these are observed things. You can't use your Kuruk's model to model the AGB phase. Because the AGB has this very peculiar, very red, cold object that you, and there we still resort to data. There is only one group or two groups in my knowledge that calculate theoretical models, atmosphere, one in Sweden and one in Vienna, but they do one model at the time. You can do a population synthesis. So this is the second ingredient that you need to use. And the third, which I want to go fast on this, is how your prescription vary with metallicity of the population of your galaxy. And here I use theoretical prescription back to a work by Renzini et al. In 1981, which is consistent with work by Paolo Marigo, 1996, which tell you that actually carbon stars are far more abundant in low metallicity population because there is less oxygen. which we also learn from Alexander. So you have more free carbon, so you have actually, you should expect in low metallicity galaxy much more of these things, which could be interesting for high redshift. And the more you increase metallicity, the more the available carbon is got to do CO, and you have less pure carbon stars. So this scaling also is something we don't disagree, but I think it would be good to have actually calibrator at so different metallicity to check. So, if you do all this nice theoretical modeling, what you come out is with the following plot, which show the following. This is a 0.8 billion year single burst. The black is my standard model when I do not put the TPAGB, and the red is where I put the TPAGB. So you see, popping up for the pleasure mostly of the Brazilian researcher, and I want to acknowledge all this community for this, you will understand in a minute. You see a lot of features that you will not see otherwise, some of which, especially C2, should actually only be featuring, very difficult to obtain observationally, I'm told, but the C2 is only present in carbon stars and should be a feature of 1 billion year population. The other thing that you see is that you have near-infrared flux. No surprise, you have red stars, they give you flux. The clue is they are not old, they are like 1 billion year. And of course, the debate in this paper that Laurie mentioned yesterday was that the models that were available at the time were much lower in flux for the same age, all of them. Highlighting that the conspicuous part of the TPAGB was actually not included, and that's why mine were very different. So let's come to glorify this country. In 2006 at the IEU, I was approached by Miriam Pastoriza, whom I didn't know personally at the time, saying that she and her, at the time student, Rogerio, had a series of spectra that they couldn't fit with any existing model except mine. Cool. I was kind of happy with that. But you see why. These are near-infrared spectra. I need to say that they had the best observational data. In Europe, we had no idea about those data. Which telescope was that? Do you know that? So, but see, really something we have never seen, because what you see, people thought that the near-infrared is boring, like a rail engine's tail, quite smooth. No, it shows a lot of bumps. And in order to fit those bumps, you need the stars with bumps, and these are AGB stars. So that was the thing. And so they published this in a series of papers in 2007 showing this, and then you see Mara Martins actually claim to have detected even, yeah. IRTF, okay, where is it? Mauna Kea is in Hawaii. But you have a privileged access to that. We didn't have, I mean, these things were really a surprise to the galaxy evolution people. Remember that this is what the James Webb Space Telescope will look at. But at the time, it was, how do we fit these things? So this was quite cool. This is a recent paper by Riffel et al. 2015. I report the title, and Rogerio told me that he was obliged to put the question mark by the referee. Because of course the referee was annoyed. Very pushy use of literature. But what I wanted to show you here is similar to what Natasha showed me in her poster today. You start to fit the observed data, and you get the star formation history. This is important for what we do tomorrow. One parameter, you look at the chi-square, how well your model fit the data. Fine. But the other thing, what do you get? Does it make sense? That's the other thing. So what they have fit here, you have two models, my model at a higher resolution and the BCO3 model. The chi-square is marginally better in my case, but I would not bet my salary on this thing. However, what you note here, you get a smooth star formation history, while here you get a clump with nothing in between. It's like your galaxy stopped here, nothing at all has happened, and then a bump there. That's only the AGB, which is actually in the middle. Because the model don't have it, they cannot fit well, and so the model is forced to run up on ages that are outside that range, and this gives you a sort of bumpy star formation history. So it's very important. I think Roger is very serious because he shows every step of his work. While in other cases of extragalactic people, you get a result with major implication of galaxy evolution. And you should wonder what is behind. Does it make sense, or is a fudge solution in terms just of statistics? So I want to put this as a comment. Now, the actual boost that I promised was the Redshift universe. So these are all actually, it's nice that it works at all redshift. These are redshift 0 galaxies with ongoing star formation. This is from this paper by Cimati et al. Redshift 2 stacks, 480, I don't know, many hours of spectroscopy of GMAS in redshift galaxies, and the fluxes that you get, oops, I didn't want to go that fast. You get a lot of high near-infrared fluxes that are all the points. And what they've done was the same thing, was to put the classic BCO3 model for the same age that is consistent with the optical. So in this sense, they fixed that. And you see that it lacks near-infrared. My models are the blue. I don't understand why. My models that are the red are plotting blue in this paper. Which, no, this is, I mean, I don't know if your supervisor will always tell you that the color of your plots matters a lot, such that the reader really get the message. So I would say they should use red for mine and blue for them, because these are bluer. Sorry for the side comment. The green in between, I know that you are hungry, we go to lunch, so I try to keep you. The green in between was a model that Gustavo and Brusual, Charlot and Brusual edited in 2007 in order to increase their AGB, because this discrepancy were quite sizable. And I will show you why there is no way that you cure it with imposing AGN, imposing dust. There are things that simply those galaxies will not host. So we were very happy about the fact that redshift 2 and 3 galaxies show really big in near-infrared fluxes. This is the glorious stellar evolution from my point of view. These guys have shown the same case at redshift 1, so down to redshift 1, in fitting other galaxies from a complete independent survey. So there was a conspicuous sort of consensus that without the TPAGB, you don't match a CD of galaxies. But of course, when life is going very well, comes the problem. So these guys, at some point, publish a paper saying, no, it's everything wrong. The calibration of the Marastron model underestimated the ages of the globular cluster. Okay? In fairness, in '98, I got the ages that were published. I didn't derive it. So I used what was published. So I can accept that in 20 years, ages changes, but I will show that this is not the case. So what they have done in this plot, they have recalibrated, they have redone my calibration plot, a bit cheeky because they use B minus K instead of the bolometric, which instead is what you should use. And my model is the blue, and their model is the red. One is there, one is BC, and the data are those scatter points. So you see that they have pushed my model, they have pushed the data to become older. So they are here instead of being there. And the other thing they have done, this is important because it is still to be understood whether it was the right thing. They have binned the data that are the big diamond. Why they have done so? Because they thought, I also bin it here. This wanted to be the arrow bar. They have done another binning. Not believing to data of individual cluster, I may agree with that. They have compressed clusters, which they think had a similar age, into one supercluster, whose value goes much lower, because it benefited from cluster that had a smaller And so at that point, it seemed that due to all the data, this is the way people wanted to accept it, I have overemphasized the contribution of the TPAGB. So if you are a serious scientist, you react in a good way. Change your model and see whether this suggestion works. And now I can tell you the final end of the story. Yes, but I need to finish. Because we had questions. I know, today, but this is so tricky that if you present it sloppy, then people don't understand. Thank you, Laurie. Yesterday I did a good job. Today will be less good. So what we have done in this paper, we have essentially squeezed down my models, which are now circulated as I'm in preparation, and I'm not sure I will publish them, but I tell you why. Because, yeah, for 13. Yeah. Now, so what I've done here, in this paper we show two things. First of all, the age claimed by Conroy is incorrect, grossly. Okay? This is a calculation that especially Alvio Renzini and Laura Greggio have done. Their billing of ages was incorrect, and the AGB phase transition still peak at 1 billion year. Why it was uncomfortable to have these ages? This is 3 billion year. It imposed a star formation history of the Magellanic Cloud, for which most clusters are pretty old. And then if they are so old, why should they have carbon stars? I mean, people see carbon stars. You don't have enough envelope in those masses to get a carbon star. So these ages were uncomfortably old. Over the lunch, I can tell you how they derive it. Here would be too long. But in this paper, we confirm that the 1 billion year is instead the age to obtain, even assuming their tracks and their error bars. Instead, their binning implies how much red you go, and my model are still on the upper envelope, and you can reduce them. So here, on purpose, I force my model to be less red, so this M13 version is the same model in which I quench by a factor of 2 the TPAGB fuel. For fun. Let's see. Assuming, sorry, which I don't want to assume all the time, that the Magellanic Cloud Cluster data are complete enough, or say enough, that I can go so sophisticated and following this line. What was the next step? To fit a redshift galaxies again. The same galaxy that told us that the TPAGB was required, because that was still there, right? These people have not shown that that was not the case. So what we have done in this paper, we have accumulated a very large sample. When I say large, is in high redshift, getting 58 passive galaxies, passive in the sense not strongly star forming, so the same type, is the largest sample available, and especially they have spectroscopic redshift, so we know their distance. That's another side comment. Some of the work that don't find this AGB have photometric redshift, and the distance and the strength can be traced, but this may be too complicated for the student. Let's now believe that these are good data from HST, Spitzer. In this paper, we refit the galaxies with all the models. The red is my standard model MO5. The gray, how unfortunate this color, is the M13, the one with a bit less, and the blue is the BCO3. And what we plot here, one of is the chi-square, I believe is the first one. The last is the stellar mass. And you will see exactly the same trend as we saw in 2006. So, living galaxies spanning a wide range of star formation history without dust, my 2005 model always get the best chi-square, no matter what. The M13 with less TP get a bit worse. The no TP at all, BCO3, get the worst at all, completely. Okay, so that hasn't changed at all. But now, instead, and this I show in a table, if I allow reddening, and this is something we discussed over lunch, if I allow reddening in these galaxies, and I will give you a clue later, then actually, these are the fraction of best fitted galaxy. The BCO3 get the first ranked. So when I allow as an extra parameter reddening free, so it can be anything, AV of 3, then this model get jump up. So this is the line without reddening. Look only at these things. Well, my model gives the majority of best fit, and the situation a bit reverse if I allow reddening. This was the same in 2006. At the time, we argue, okay, we don't have measuring actual dust in this galaxy, but the discriminator seems to be, do this galaxy contain dust or not? Because for people doing model, it's fun to put an extra degree of freedom like reddening, but they give you a galaxy that does not exist. Now, before we go for lunch, what do you think is the answer? Is there galaxy? Is there dust in these galaxies? Well, I would not be so smiley if there were. No, but I want to show you that because there was a work that I told Thiago yesterday. Alison Mann actually measured the dust, finally, using far infrared instrumentation, Spire, Herschel, I don't know, whatever. They did stack, and not even in the stack, you could not find neither cold nor hot dust. Very consistent with the fact that these galaxies are selective, non-star forming. So why do you want to push so much dust in an inert galaxy? So, finally, and this is really, I think this is the state of art, when we impose to cut away the solution that are too dusty, the formal fit solution, then the situation reverses again. So it was only the reddening that have polluted the discussion on pure stellar evolution. It can only be possible now because this instrumentation have observed exactly the same sample of galaxy. When you fit a distant galaxy, we will see tomorrow, you can go, you have freedom, right? It depends on which wavelength range you fit. You can get different results. How you constrain that, you either believe only to the statistics or you think, well, okay, let's see whether this galaxy really feature that. We can do this now with the dust. So I conclude now, and I conclude the talk. This is a very interesting thing because I'm afraid all the claim against this for high redshift don't work, and we have tested, including my models where I reduced down the TPHB. Now there is a very interesting difference between clusters and galaxies because the Magellanic Cloud cluster shows this fuzzy signal, especially with latest data. So this can be, I have an idea on why this can be, but I'm not going to tell you now because we want to go for questions. But I think this has clarified a lot of misconception in the literature. Thank you, guys.
Thank you, Claudia. Is there any question for Claudia?
Is it working? Yes. Well, I have many questions, two at least. Reason that the clusters you use for calibrating the models are those in the Magellanic Clouds.
The age span, there are three groups of Magellanic Clouds. You have very young clusters. I will show how you can do UV studies that are less than 100 million years old, group of 1 and 2. Then you have the 3 and 4, 5 that are between 400 million years and 2 gigayears. And then you have got the older clusters. In the Milky Way, we don't have clusters spanning the AGB. That's why you can't use the Milky Way. The only thing is the Magellanic Cloud. Yeah.
Said as well that, correcting something you said, that it's only the globular clusters that you use there?
No, because if I am, the globular clusters are held to be the oldest one. That was globular, well relaxed, or whatever. For younger cluster, people use a star cluster in general. Was the only correction I wanted to make to myself. All right, because there are clusters that you would not call globular, but it's the same. What you need is a populous cluster, because if it is too small, you fluctuate, it's like mad. M67 is decent even if it is not old and is not strictly a globular. So it depends which object you have. The Magellanic Clouds, one has to be careful because some are very small mass. You can change, yeah.
There are recent works that show that there are high star formation rates in elliptical galaxies. So is it explained by your models?
Which works?
I think Lohi works on it. No?
Not in local elliptical, certainly not.
It's elliptical.
Sorry? okay. Well, okay, we need to do the
Yeah, so no, it's special ellipticals that we were showing that they are actually maybe rejuvenated, and it happens in cluster, in dense environment, like in Virgo and coma clusters. And so I was going to ask you to talk before to actually, it's very hard to derive star formation rate for these types of galaxy because since they are elliptical or early type galaxy, but then they show they have some signs of star formation. So to derive the correct star formation rate, we need to know more about them. So I do your input on that.
So the model can give you any type of star formation. It's not biased to have elliptical being old. It's the other way, that applying the models to general big ellipticals, which I'm sure is not the target you're thinking of, then you always get old ages. And this is not only what we found, but it's pretty accepted. There is a distinction in cosmology that I would like to make between ellipticals and elliptically shaped galaxies. It has been demonstrated in the 70s that anything you merge this with me, you get an elliptical. There is a reason for that. No, seriously, this is what Joshua Barnes would show you, okay? There is a bit of relaxation time, some tails, but it doesn't matter. At the end, you get a ball, which makes sense. But the biggest elliptical, those that are above 10 to the 11 solar masses, those instead must have another origin. Okay, and the fact that you find the residual star formation or rejuvenation, actually we find it as well in 2016, in 2006 in a sample of Sloan, Shavinsky et al. There is things. It usually is the lowest mass early types, so 10 to the 10th. And this can be because they might be lenticular or post-merger. This can happen. Okay, but now stick to the model instead of my strongly opinionated view of galaxy evolution, which I'm going to give you. The model are flexible. You apply them blindly, as I've done here, and then you see what you get of a result. If there is star formation, the model should be able to tell you.
So on your last point, that's the first on the summary for the dust in some of these galaxies, maybe a high redshift, maybe even a low redshift. Some work that we discuss a lot in our papers is the SED fitting that Samir Salim did for some of the galaxies, I think at intermediate redshift. And what he sees is that he can fit the modeling for he can do a pretty good SED fitting and extract some of the extinction data for the star-forming galaxies, and that works a little better. But if you go to the even Green Valley galaxies and certainly the red sequence, if you apply that blindly, you overestimate the extinction. So I think that relates to what you're saying, right? So is that the SED fitting with extinction works fairly well for blue or very dusty galaxies? Yeah, but the other ones you overestimate the extinction by quite a bit.
Yes, it's either you overestimate the extinction or you get other properties that then don't match what you. I agree with you, and we'll see tomorrow some mock galaxy experiment we've done to see actually whether the property you derive are robust when you know the entry properties. The reddening should really be used with care. But I wanted to say the reddening couples more with model with low TPAGB. Because it is no surprise, all the fit we have done, in my model there was never a best fit with reddening over the no reddening one. So your generosity in using reddening must also be coupled with which model you are adopting, which physical model you are adopting, because that gives you different results, it has shown.
You showed at certain point a comparison in between your models. I think that it was Charlotte Brussois 03. And you had the blue, the green, and the red lines. And I didn't understand what they did on 07, in fact. It was their model. This one, I didn't understand what they did in order to push the green model to...
This is a plot. I have not participated to this paper. No, I want to stress this. So I'm not biasing. What they have done is to take this classical grid plus Charlotte sent them the CB07. We discussed yesterday with Chago that CB07 is still being circulated since '07. What happened there? Because they noticed and they took it seriously, more seriously than their users, that there was a sizable effect. They told me once, I know this cannot be explained by dust or AGN. They have push up the AGV, okay? Outside the Padova tracks they were using, because then Padova re-emitted tracks with more TPAGB. This is Marigo et al. 2008, also simulated by these results. How exactly they have done that, I don't know, because they have not been published. However, it seems that they are particularly, you see, they it's more red, so somewhat they have manipulated those phases, but I really cannot say more.
So going back to the elliptical things, you were mentioning, you were like stating the different star formation for the complex combined model. I don't remember. You were saying like the different star formation rate possibilities. And so from my understanding, you were saying that for normal or elliptical, not rejuvenated or anything, it would be more the truncated part that will work the best?
Yes. Yeah, that's a... So, the big ellipticals look very old in the local universe, okay? If they have some blue or UV light, it's the UV upturn and it's not young stars. So, if you want to make an evolutionary model from high redshift, which I will show, you make a truncated, you have a burst of star formation, conspicuous, very high star formation rate, for a relatively short time. How short the time is, I will show you, correlate with the chemistry you want to obtain. As we know, elliptical are alpha-enhanced. That time cannot be longer than 400 million years. So it's a short time, and you cook your 10 to the 12 solar mass galaxy, and then nothing will happen to it. Instead, small mass early types, they can be quiescent, and then at some point they get rejuvenated by something entering some dust, which can be your case. And then you will have an old guy. So how to model, this is something we want to discuss tomorrow. You can still use a passive model, because it has done 10 billion years of evolution, plus you put a recent burst of star formation, which is putting an SSP with a younger age. This is the most logical thing to do. Yeah. Instead of an exponentially declining, because that's not the case. That is a gentle way of declining star formation and not a secondary burst. Exactly.
And the physics behind, you were saying that you have different, we don't really know what quenched galaxies, there are like different scenarios. Would that affect the truncated part, depending on what is quenching the galaxy?
So the best way of quenching a big galaxy is just to let it consume all the gas. But this was said by Sandwich. I mean, it's all things, right? It's the monolithic collapse things. You cook all the gas because the star formation efficiency is very high. You have supernovae, but the potential well is large, usually, in this galaxy, so the product don't escape. If you put the same in a small mass galaxy, then there will be copious outflow because the supernova will eject the remnant. So that is... So you can do this, but people in semi-analytic model, they cannot achieve that, so they impose an AGN feedback. So an active galactic nuclei in the center truncates star formation. It's a bit of a fix to the model at the moment, because you need to have a powerful thing. So to me, it's not, I know that the literature is brainstorming on how to quench these things. To me, it's a quite simple way. It's more difficult to restart the star formation than I think. Yeah.
Is there more questions? No? So we can thank Claudia again. Thank you.
So the people who are going to present their posters, please don't leave. We still have your peers, your fellow participants. I think 3 of them will be presenting.